Hi everyone, I'm Jiapeng from Southern Methodist University, and today I'll be presenting solving inverse problems using self-supervised deep neural networks. We gratefully acknowledge support from DARPA-DSO. Solving an inverse problem is the task of computing an unknown physical quantity L that is related to a given indirect measurement M via forward model P. Imagine we blurred an image with Gaussian filter. If we want to get the sharp image back from the blurry one, we are solving a linear inverse problem. Various inverse problems are involved in computational imaging, and the presence of noise in the measurements makes them more difficult to solve. Our group is interested in three examples: computer-generated holography, face unwrapping, and indirect imaging chorography. The three practical problems listed above have the same goal of recovering the face from measurements. If we want to build a lensless projector, in which the illumination pattern is given, and we need to figure out how to modulate the delay of light, we can solve the computer-generated holography problem with the traditional Gershberg-Saxon algorithm, or a data-driven learning approach. When processing radar interferometry data, we need to unwrap the interferogram because the 2-pi phase ambiguity in the signal. Minimum cost floor algorithm is the most commonly used method for inside phase unwrapping. In non-line of sight imaging chorography, we can measure the spatial correlation of image, but what we want is the latent image itself. Analytical methods struggle to recover the latent image from noisy measurements, while learning method can solve it in a data-driven style. The analytical method, for which the problem is explicitly defined and domain knowledge engineered into the solution. The approaches for each problem have very little in common. Deep neural networks usually do not benefit from such prior knowledge, and instead make use of large datasets to learn the unknown solution in an end-to-end fashion. What if I tell you that all three problems can be solved by the same framework in a plug-and-play manner without using any training data? Unlike data-driven learning approaches, the generative neural network in the present framework does not have direct contact with the measurements. Instead, a fixed feed is fed to the network. The generative network model f theta is matched with a task-specific physical model P that maps the domain of generative model to the space of observable measurements. A loss function L measures the deviation between the predicted measurement M hat and the observed measurement M. Through the backpropagation, the gradient of the loss function is used to update the network's parameter theta associated with the generative model. Following many iterations under the physical model's supervision, the generative model learns to produce a latent image representation that solves the inverse problem. For instance, in solving the phase unwrapping problem, the measurement is the wrapped phase. We simply choose the physical model and loss function according to domain knowledge, and pick whatever neural engine you like. The unwrapped phase will be recovered by optimizing over the space of network parameter theta. Inverse problems, including but not limited to phase recovery problems, can be solved with the same framework embodiment. The only difference is the choice of physical model and loss function. In conclusion, by simply pairing deepness with appropriate physical models, our work takes the first step towards developing a unifying modular framework for solving inverse problems using self-supervised deep neural networks.